Okay, I'm going to pause the recorder here.
As am I. That's my problem, too.
You figure it out?
No, I'm saying that's my problem, too. I can do the labs in Linux easy because I have the NCPR out there.
But with WebEx, I'm kind of limited. Okay, so we got an agenda today. I want to do a quick health of the system check on the 4 Floyds. I need to get into the performance evaluation. When I mean performance, I'm really getting into the time domain, the time command, or CSA, or PBS data. And part of the things I need to do is a workload characterization. Again, the more I know my workload characteristics, the more responsible my configuration decisions are. So part of the lab, I've given you a code 1 to code 9. Again, on Monday was kind of an overview and get the system together, get instrumentation turned on, figure out what you have, do the inventory. Yesterday, I tried to focus on just analysis and live analysis tools. Today, we're moving into applications now. So we need to figure out what our applications are. Each of these 9 codes is unique. One is big CPU, one is big memory, one is big I/O, one uses SHMEM, one is MPI, one is metadata intensive. Those code 5s that we were running is a program on the web called Postmark. And Postmark is meant to emulate a metadata storm like an email spam attack without the network load behind it. One of these programs is using SHMEM. So again, I want to get a characterization and figure out what these 9 codes are. I want to know how much CPU, memory, and I/O they do. And from that, I'd like to classify them in terms of big CPU. What are the resources they need? Which are the big CPU ones? Which are the big memory ones? Which are the big I/O ones? So again, I need to know more about my workload. I also want to get a little bit of baseline going, which means I want to get SPV working. And Camille, I gave the tools to you in the prior class. I'd like to try to make sure you can get it running this week. And the other thing I want to do is Ganglia and get those ready. Then we got to talk about applications. And there I want to talk about Intel compiler install. I also need to cover the module command. And then we need to talk about profiling code 2 single-threaded. Tomorrow we're going to multi-thread it. So in profiling code 2, we're going to look at the gprof, which is a GNU profiler. I want to look at compiler options. Actually, I should say Intel compiler options, including profile-guided optimization. And then I want to profile it with the perf utility, which is a Linux tool. And then I need to get into PSRun and the NCSA perf suite. And beyond that, then I need to get into PAPI, hardware counters, and in particular, there is a psrun-c perfx.xml file for a hardware counter report. Perfx was a utility that we had on IRIX, and it's going to give me like 31 counters. And we're going to have to install this, and we're also going to install the Intel compilers at this point. And that's kind of the agenda for the day. So tomorrow then we're going to take code 2 and multi-thread it with OpenMP. Take a look at that. Then we got to look at code 6, which is an MPI application, profile that, and then move into CPU sets and dplace and get PBS Pro working in a CPU set scenario. So that's today's agenda. Any questions right now? So let's start off here. I'm going to go to my desktop. I'm not really interested in PCP right now. I just want to go in live. Again, you don't always have graphical tools. Yeah, I've been trying to get you to learn to use PM chart, but the main reason is I can get all this data and correlate it and jump between my different plots to see if this is going up, how is that affecting other things. The hard thing here is that when you're looking at something, you can't see the other things. You can only see one thing at once. So that's why it's nice to be able to save an archive with PM chart and be able to get that all display that had CPU, memory, I/O, networks, NumaLink, per node information, and I tried to build a simplistic all type of report yesterday. Don't be afraid to grab that from Floyd 4. Root password was SGI, and it was in /root.pcp PM chart. That's where your custom views are. Now let me get back to that. Again, I don't always need a graphical interface, but PM chart is especially useful at looking at the memory stack and stuff like that. So let me just start off with Floyd 1. Oops. I don't want to do that. I want to go in as root. I do not want to go in as a user and then SU to root. The problem with that is if I'm trying to look at a load situation and I log in as an end user, and in my case I'm a NFS home directory, if I have any network contention problems, that guest login is going to slow down the shell that my SU to root is seeing. So I don't want any contention there across NFS or anything. Also, and this is particularly for Brian, the field diagnostics RPM was loading the MPT module for some diagnostic tests. But I ran into a site where MPT was NFS mounted across their cluster. So you logged in as root and you had an NFS path. And if you did anything, just typing in LS or PWD, it's going to go through that path and it would hit an NFS server that wasn't up or running, and they couldn't even log into the system as root to be able to get in and fix that. Does that make sense? Cleaning up your path and making sure that you got as short a path as possible. And also that's the advantage of the module command. You don't have to put stuff in your path unless you need it. Let me just see what my path is. I got SBIN, user local SBIN, root bin, user local bin, all that sort of stuff. I could get rid of this stuff, games, for example. I don't know what might be in those, but I don't have an NFS-mounted file system in this path. Okay. Topology. So I got a 32 CPU system, about 128 gig of memory. Again, I'm not going to worry about how these numbers add up. That one's saying 126. If I do a node info, it's going to do it on a per node basis. And down here in the total, it's giving me 134. 33 gig, and this is per node, 33 gig. I should say per socket. Okay. Get out of there. So 32 CPUs, about 134 gig of memory. That's kind of rounded down. On a given node, 2 sockets, about 33, 66 gig. Adding these up here. And again, if I do a DF, I do have an SDA4, and in particular of interest to me right now, SDB1. which is this data to file system, is showing 100% full. And if I do a df-I, this thing is also out of inode space. And I can't do anything with that file system right now. So I was doing a quick inventory here to figure out what I got. So now let me just start off here. I'm going to do SAR 1 space 5. And I see the system is about 65% user time. Let me do a SAR. And it's been running that way since midnight. Let me go into var log SA. Today's the 17th, SAR-F on SA16. And it looks like that thing started up about 10 o'clock last night. Before 10 o'clock, I was in the 6% CPU utilization, mostly idle. Everyone with me? So I got some sort of load that started on the system at 10 last night. And again, I'm trying to correlate data. So that's SAR. Let me do a SAR-R 1 space 5. And my memory looks fairly healthy. I only got 46% of my memory being used. Half a gig, though, is raw I.O. And again, I've got 58 gig of cached. And remember, I keep stressing what's in that cached field, which includes a lot of different things. So I want to break that out later. So CPU, memory, disk. Let me do a SAR-DP just to go from midnight. I do see SDA is kind of busy. Borderline here, it's only 10% busy, 30% matters to me. But I'm also seeing an average wait time that's too high. There's almost an average of a half a second. Those are in milliseconds there. Almost a half a second of the average wait time. Now, I was looking here, and here I can see, let me actually do this now. SAR-DP, pipe grep SDA. Let me try to get rid of the wrap here. That's not quite it. Let me drop my font down. Sometimes it's real hard to work with this raw data. So now when I'm looking at disk drives from midnight, let me put a head on this thing. So here are my transactions per second. It looks like something started at about 8:10 in the morning. Number of read sectors, it looks like I'm mostly writing here. Average request size, they look like large requests. These are in 512-byte blocks. I also have a high queue size. Lots of I.O. operations that are queued up because the drive is busy. And look at, during this interval, the drives were 95% busy. And then here was the average wait time in milliseconds. I want that less than 60. Here I'm even looking close at a second for an I.O. operation. Now, this is not a, don't take it too literal. In other words, I am not caring that these things don't balance. Like with memory, I was not caring that they weren't perfectly matched. And I'm not going to take that too literally as saying that that's a 9/10 of a second average IOP wait time. But I am going to use that as a red flag saying I'm above 80. I may not believe it when it's in a 30-second range, and I've seen these things go into 30 or 40 seconds. And I'm just going to say, okay, it's big. I don't care if that's a perfect number, but it's a red herring flag for me to look at. Now, this particular I.O. event appears to have gone from 8:10 to about 9 o'clock. Okay? So I was trying to get a reference or a baseline, and there was something running ahead of that. I'm just looking at the columns here, and this column right in here, we had writes going on the whole time. So there are writes going on here. Very low bandwidth, though. And if you look at the average request size, they were small as well. I'm going to bring up top disk. And I don't see any activity on the system right now. Now, top disk is going to filter stuff that's quiet. So if it's less than like 3%, let me do a man on top disk. And there is a, sets the threshold for percent active, top disk dash A. Let's go 1 and see what that gives me. And now I am able to see SDA's activity. And I specified a 1, but it's still showing it as a 0.4. So when I came up by default, I was not able to see the disk activity to SDA because the percent active was too small for it to be above the threshold. But I can see my disks are generally writes. I'm doing 5 KB writes there. Okay, so I got stuff on CPU, I got stuff in memory, I got stuff going on in I/O that can take a look at things. So I'm going to pull all those apart, but I want to finish my health of the system first. So CPU, memory, disk. Now it's file system buffer cache. And for that, I have to go to procmem.info. Again, stop me if you got a question. So let's see what we got here. So there's my 132 gig of memory, 70 gigs free, but I could still have problems, particularly in a CPU set situation. I've got half a gig of raw I/O here / dev I/O, and again, my cache is the biggest thing in here. I'm seeing a 56 gig kernel or 56 gig cache here. Swap cache says that it's both in memory and on the swap device. That could include shemem. But if I look at my swap, nothing has gone to swap yet. I got no swap I/O going on. So I can't possibly have swap cached. Now I'm a little bothered here. I've got inactive. In fact, the majority of my memory is inactive file cache. So it looks like 51 of that 56 gig has not been used recently and has been aged. Again, my swap is fine, my dirty is fine, my write back is fine. I get into those more in the second week. I will try to pound on them when we get a chance. My application space, real small, 200 meg, that's real small. Mapped is shemem, and this is telling me that there's nothing attached to the shemem. I do see some stuff here. And I got a 2 gig slab, and most of that's reclaimable. So it looks like I got a majority of my cache that is not being used. It's not shemem. It's probably just cache clean, stuff that is written to disk but has not been thrown away yet. When I write to the file system, it's going to go from dirty to write back to clean. And if I don't remove the file, it's going to stay in cache as an inactive file space. And since it's inactive, that means that it is not open either. So my file system doesn't look too bad. I've got a 2 gig slab. My buffer, half a gig, which I can free up with BC free. My file system buffer look okay, but my cache looks big. And again, the cache looks like it's inactive, clean file cache that might not even be open or being used anymore, and it's definitely not shemem. And keep in mind, shared text is in this field as well. Again, I got no NFS traffic going on. And the rest of the stuff, by the way, is a don't care. All the stuff on the end, you do not care about it. These are for virtual swap off. By default, virtual swap is on. Let me do a sysctl-a and grep for VM. There is a, where is it here? Overcommit. I'm looking for the overcommit. There it is up there. Overcommit memory. When it's a 0, that says I can oversubscribe, over-reserve, overcommit my memory. Again, we're going to talk about memory tomorrow or Friday, but we have to talk about reservation versus allocation. A 0 says I can over-reserve my memory, I can overcommit my memory. And this is the ratio, by the way, of virtual to physical. So let me take a look at these numbers while we're looking at it. So I have a commit limit of 76 gig. And only 873 meg, 873 meg has been reserved. This is the reservation that I have on the system. This is the amount of virtual memory I can reserve. Now, by default, it's half of the physical memory plus swap. So if I take my physical memory, which is, let's just say it's 132, okay, so what do we got there? 66 gig is half of that, plus the swap of 10 gig gives me about 76 gig, and that's what I have here. And again, that 50, where was it here? This commit ratio said 50% of my physical memory. So let me do something here. sysctl-w VM dot overcommit underscore ratio equals 100. Now let's take a look at the procmem info. And now my overcommit limit is 142 because I set the ratio to 100% of my physical memory plus my physical swap. So I now have a reservable virtual memory space of 142 gig. But again, I can overcommit my memory because the overcommit is a 0. If I set the overcommit to a 2, then I'm running with virtual swap off, and basically I cannot reserve more than I physically have. These two fields here are part of the SAR-R report. And frankly, they're pretty useless. I would have not have put them on this command option. So here's what I've committed. 114, and that's what we have. Well, let's see. One point one gig looks like is committed, and I'm not sure why there's much of a difference here, but I'm less than, this is committed, but there must be something else added in here, like maybe the slab. The slab must be added in the commit field these days. Let me do something here, SAR-R since the beginning of the day. And you can see what the commit or the reservations have been. I'm going to do a user lib64 SA1 and write a record in there. And I guess you really can't see the reservation going up. I was trying to see, there we are at 113 now. But I can't really see what the commit limit did in that. The ratio is too small to really spot it, as this is the percentage of the virtual memory that has been reserved. So again, that is basically this divided by this. Okay? So again, those are don't care unless overcommit is a 2. These are static. They never change. Ignore them. I haven't ever used this one either. And I don't care about any of these unless we're using huge pages. Purpose of a huge page is to reduce TLB misses. We'll try to talk about that Friday. Okay, let me just see if I'm still in the same situation. So 132 of memory, 70 gig is free. I have a 56 gig cache and a 2 gig slab. So I was looking at CPU memory disk, file system buffer cache. Now it's IPC, so I'm going to do an IPCS-AM. And ooh, I do have a problem here. M, pipe WC-L. I've got 4,100 entries. Oh, I see PBS is in here, my desktop is in here, but I got all these other entries in here. They're real small in size, 32K, but notice they are not attached to anything. Also, if you count them, and this is all guessed, okay, so if you count them, there's more than 4,000 of them. Now, sysctl-A, grep for shmem, we have a limit here. The most you can have is 4096. And if you add in the inline and the header lines and stuff like that, you're basically hitting 4096 of these IDs before you get a failure. The database market, we often have to up this one. This one, by the way, is the maximum size of a shared memory segment. And that's in bytes. And it's basically unlimited, bigger than we physically have. This one, however, is in pages, and that's the total amount of shared memory that can be used. And it, by the way, is bigger than physical memory as well. Basically, neither of these are actually putting a limit on the system. So I have a problem here. Let me try to run something here. I'm going to run this use shmem thing, and it says, cannot create or get a shmem segment, no space left on device. Notice those applications did not run. Let me try just one of them. The first field is the size of the shared memory segment. The second one is the ID that they're going to attach to. Oops. And it says no space left on device. I'm going to try an strace. Good enough. I'll often dump it into a file. Now, one of the problems with strace is it's really verbose. You cannot sit there with strace and read it line by line. This is a fairly short trace here. Didn't spend a whole lot of time trying to find libraries or anything like that. But these things can get really verbose. But right in here is where it tries to get a shared memory segment, and it's getting a no such file. So then it tries to create it, and in the creation process, no space left on device. And that means is the IPCS-M. All of these things, all the IDs have been taken. 4096 was the limit. Any questions on that? So I'm going to clear those up right now. And I've got a script. Basically, this was a memory leak. Let me show you the script here. It's going in and cleaning unattached shared memory segments. Now, you need to know your market. In the real-time market, it's possible that you have an application that generates a shared memory segment, exits, and then something else will come along and attach to it later. But a majority of the HPC market and the PBS batch type of market, you don't leave unattached shared memory segments around. Gaussian is known for getting killed by PBS and then leaving shared memory segments. Most sites I get to that have Gaussian will discover unattached shared memory segments from aborted jobs. So I'll show you the script here in a minute. Some sites will put this as a cron event to clean up unattached shared memory segments. But again, you need to know your workload. It is up to the program to release shared memory segments when it's done. Normally what you want to try to do is in your program, you want a signal handler that's going to get a sig term, and PBS and torque and stuff will terminate a job with a sig term. The application would have a signal library call that says, if you get a sig term, jump to this routine. And then in that routine, you can close your files, you can write checkpoint files, you can remove all your shared memory segments. So now I've got all those shared memory segments cleaned up. And now this thing is going to run correctly. So here's where it actually did create it. Okay? But now I'm going to control out of that. Notice it looked for a prior shared memory segment with this ID. It wasn't there, so then the logic of the code said, let's create it, and here's the size with the ID that was basically passed in by the command line. And then we attached to that shared memory segment, and then we did a get. So now if I do IPCS-AM again, notice that I did abort out of that thing, and it never had a chance to detach from that shared memory segment. Let me cap the clear shemem script. So all it's basically doing is running the IPCS command, looking for column 6, which is the unattached field. Column 6 right here. And if that column 6 is 0, meaning it's unattached, then I grab the ID in the second column and remove it. So let me just do that again. So there we can see it detached or deleted the one shared memory segment that had nothing attached to it. Any questions right now? It's up to the application to make a library call and say, when I get a signal number, jump to this function. So let me do something else here now. There we are. Oh, I don't want to S-trace it. Oops. Okay, so that thing's running. I'm going to Control Z it. And it's now stopped. PS shows that it's still there. Everybody with me? So if I bring up top now, notice it shows that I've got a stopped process. By the way, I can spot now these code 9s running that were part of my 65% CPU utilization. I got a 63 gig cache right now and 67 gig free. Nothing out on swap. Okay, now why isn't that one code 9 that I just fired up in top? Because it's sleeping. Normally we're sorting by this field. Let me try a Shift-O. And let's try sorting by something else. Actually, I probably don't want that one. Let me do a question mark here. I want to do a reverse sort. Let me do a Shift capital R. And I'm still not catching it because it's, let me do an I. And now we've got all these individual worker threads and we can't see anything in here. So I can't see that program. But I am going to do a PS-EL pipe grep T. And there's the process. Anything that is in a stop state has a T in it. Let me do, I've got this other code 9 GNU here, PS-EL, rep 29984, and that one is running. I'm going to do a kill-L, and the Control-Z basically put it in the background asleep with the stop. So I'm going to do a kill-19 to that PID 29984. And now if I do my PS-E and grep for TT, I can see that other one is also sitting there in a signal handler. And it's at a T. Any questions right now? Bring up top. And I see two are stopped. But again, I can't see them here. I'm going to quit out of there, do a top-B-N2 and pipe and grep for code 9. Oops. And I'm only seeing the running right now because the way the top RC is set up. I'm going to remove, let me just go back into top and try an I. So now I can see all the sleepers, I believe. Let me try another I. I'm going to do a Shift W. Quit out of there. Let me try the top again. And this time I can see the two that were sleeping. And I can see the T there. Again, they're not visible in top because they're not running. We're sorting by this by default, and they're down in the 0 range. Any questions right now? So I want to do a kill. I'm going to do a kill on 29984, for example. Let me do the PS again. And it's still there. When you're in a stopped state, you don't get signals. The signals are masked or blocked right now. The correct way to handle this situation would be to continue so that the program can see the signal, jump off to a signal handler, close things off, write a checkpoint file, clean up shemem. I need to send an 18 to that thing. So when you see this T, don't just do a kill or a kill 9. Okay? You want to do a continue in order for it to see the kill. If it's a T, continue it before you kill it. That way it sees the kill signal, the sig term. 15 is the default. If I do a kill 9, it will never jump to that signal handler. 9 are not masked. 9 are not blocked, but 15 is. So I'm going to do a kill-18, sorry, 18 to continue on 29984. Do my PS again, and it's gone. Because once I said continue, it then saw the kill 15 signal that I sent, and then cleanly terminated itself. Okay, let me try a kill on the other one here that I ran interactive, 22261. Again, it didn't see the signal yet because it's in a signal handler routine, waiting. Signals are masked, and it's in a T state, stopped state. So now if I do my kill-18 for a continue on that 22261, this will allow it to come out of the stop state, the Control-Z state, and then see the signal, and then properly clean up if it does a cleanup. And notice it now does show terminated. Any questions on that? So I do still have a unattached shared memory segment from one of the kills. So I'm going to just clean that up. Okay. So going back to where we were. I've been talking for a while, so I'm just going to see if we're in the same situation. CPU utilization is about the same, no system time or anything like that. SAR-R, 1-5. Actually, memory use has gone down a little bit, not much. But again, majority of memory is my cache field, which we have not pulled apart yet. SAR-DP, 1-4. My disk drive is quiet now. SAR-DP. 948. Even at 10 o'clock, I'm still seeing SDA. So at this point, I'm not seeing any disk activity at all. Okay. Kind of hard to trace that I/O down at this point. Not seeing anything anymore. So my disk activity has changed now. I'm going to come back to that later. CPU memory disk, file system buffer cache. Let's just check that real quick. So 70 gig free, 56 gig that's cached. Most of that is inactive page cache files. Nothing out on swap, no real dirty or write back. Real small 300 meg for non-pages, 150 meg for shemem that's attached, 100 meg that is just shemem. Again, I do still have a large slab. So CPU memory disk, file system buffer cache, IPC was IPCS-AM. And again, everything's looking okay there right now. But the other one was ls-l and /dev/shemem. And I don't see anything in there. But if I do an LSOF and grep for shemem, for example, notice I can see these things are opened by the Pulse Audio and the GNOME stuff. That's the remote desktop audio stuff that's using that shemem. And I might even turn off that Pulse Audio if I don't need audio coming out of the system. Why have that noise there? Okay. CPU memory disk, file system buffer cache, interprocess communication. Now I want to do network. I'm going to do a link stat -UV 1-5. Oh, not active. Wasn't sure the other day why mine was coming up active by default. And I do see a lot more traffic on the interconnect than we saw before. We were in the 300 megabyte range. Now I'm in the 1 gig range. And then it's giving me a percentage of what that bandwidth potential is. So I'm using about 21% of my interconnect bandwidth potential. But again, in my tuning process, I want to reduce that interconnect traffic. Okay, so now I want to go to my next level. Let me just bring up top. So in top, I can see that mostly I've got these Code 9 GNU 03s running. They're 100% CPU bound. There is no sleeping or waiting going on in them. And they've been spinning for quite a while. I'm just looking at the PIDs here. Okay, quit out of there. Now, IPCS-AM was showing that I do have, well, even look at this one, 10, 12, 637 that are attached to that one. And that is 10 gig in size. So it looks like I've got 12, 637 threads, that doesn't seem right, attached to the shared memory segment. I don't have any way of catching what that would be other than PIDs. Let's see if we can get a P in here. and all we are getting is the PID that created it, 29951, and the last PID to use it, 29975. Just trying to think of another way that I can see that. PS-E, let's grep for code 9. So that's kind of interesting to me because I don't see that many attachments to it. Let me do a kill all. Code 9 GNU 03. See what happened to that counter. It's still got something funny to it. I'm not sure what's going on there. It is the prior update kernel, but not the most recent update kernel. Let's see what we've got in /proc/meminfo. And my shmem is at 100 meg. Oh, now it did go down to 0. Huh, okay. So I don't know what that artifact was from before. Why? And I didn't have that many processes, but I'm just going to have to leave that issue alone. I do not know why it was so big there. Let's see what we got for PIDs on that thing. You can also get a timestamp and see when it was attached, detached, and last changed. So this one here was attached and detached in the last few minutes. Any questions right now? When we go to top, I'm going to do an I, and that just gets rid of all the idle stuff. I'm going to do an I again. I basically got rid of all those code 9s just to see that they're gone. Mostly idle. Notice I still have a 57 gig cache. IPCS-AM. I do still have an unattached shared memory segment. Let me clear that. Bring up top. Now I do still have a 57 gig cached. Now at this point, let me go to my remote desktop here. I'm looking at Floyd 1, so let me do a PM chart-H on Floyd 1. Again, PMCD has to be running on that system. I'm going to click on this head up here, and in there I had created this all, which put all of my tabs and everything on top of each other. So there's my meminfo information. I can see my cache clean. I also see my slab in there. Not too bad of a slab. I'm going to get rid of free, and then I can see my slab is about 2.5 gig. Let me profile that for a minute. Slab top-S-C. And again, I can see mostly inodes. I got 3 gig of inodes, something called radix tree node, XFS buffers, directory entries, things of that sort. Now, when I run out of memory, the slab is the first thing that gets pushed down. But yesterday, I was in the 80 gig, 90 gig slab, and I couldn't get it pushed down. I may try to come back to that tomorrow. Okay, so I'm trying to get a reference here. Oops, put that back in the foreground.
But you're kind of going between Floyd 4 and Floyd 1, right?
I pointed it to Floyd 1. But I'm running PM chart on Floyd 4 for the GUI.
Yeah, but the slab top was Floyd 4.
Oh, you're right. You're right. Thank you. Good point. Thanks for telling me that you're alert. So let's see what Floyd 1 looks like. Ah, good. Thank you. This one's buffer head. What was buffer head for? That's for your page cache. again, we've got a 51 gig, 52 gig page cache that's inactive. Okay, and the slab here was down in the 2 gig range. So that buffer underscore head is the structure to describe things in page cache, which, by the way, includes dev shemem. If I create a huge dev shemem file, buffer head's going to grow to describe that dev shemem file. Okay? So, I want to bring back up the PM chart here. Get that display open again. I have had students that will bring up PM chart but then be looking at the system that I was doing demos on rather than their own system that the lab experiment's going on. So low CPU utilization, I do see a little bit of blue in there. In fact, it doesn't even go away. I don't know what that blue is. Swap is free. My memory is mostly the cache field, which is what we're looking at. I/O operations are real small right now. By the way, I'm going to edit samples. I want to see a larger interval here. Mem info in more detail, and again, my shemem is in the 5 megabyte range right now. Most of my memory is that cache field, and I can see a little bit of the slab in there. K-swap D, I do see some allocations and deallocations going on, as expected, but I don't see any trimming activity. These were supposed to be trims. These are supposed to be page activity. Allocating, deallocating, activating, deactivating. Basically, when a page goes inactive, it's deactivated. If I reference it again, it becomes active again. Node info, free. Most of mine are in the 20 gig free per socket, and we had like 33 gig there. Used, it looks like they're all about the 14 gig range. And again, the slab is only 600 meg across these, and shemem is only about 2 meg. So there are other things in the cache that are fairly spread out, evenly spread across the nodes. That's going to be that page cache, whatever that thing is. Numolink, okay, since I killed those code 9 GNUs, my interconnect traffic is back down to an idle state. Again, if I click on this, I can spot that one is between blade 0, but I can't see the other connection point that it's going to. That's where I need the linkstat-uv command to actually see the port-to-port connections. Any questions right now? So what I want to do here now is a BC free. Now one of the things here, LSOF pipe, let's grep for regular, pipe, sort, dash R for reverse, B to ignore blanks, N for numerical sort, and then a K to sort on column 7. This is a little trick to find out if a file is open. So if we have any open files, LSOF will show them, even in /dev. But this page cache is not open and it's inactive. And we're sorting by this field right here, which is the size of the file. So whatever's in my page cache is not open by anything either. Now that doesn't mean that something might not start and open it in 5 minutes or something, but the assets that are in the page cache are currently not being used. One of the things I missed from IRIX days, Brian might remember it, is BuffView. And BuffView was a tool on IRIX that would actually give me a top type of view of the assets and the memory footprints of the files that are in the page cache. So I've got a 60 gig cache and I don't see any assets in it that are actively being used. So I'm going to do a BC free. Now, actually, before I do that, let me do it as a different thing. sysctl-w to vm.drop_caches equals a 1. This is what BC free is actually doing, is just calling that thing. Now let's go back to PCP, and there I can see that file being trimmed. Let me get rid of free here. And you can also see the slab. If you've got slab top up right now, you'll see buffer heads being trimmed as the file is being cleaned up. Now remember, yesterday I had inodes and stuff, and I could not push that slab down when it was 80 gig of inodes that were, by the way, actively being used by the running workload. This time I was able to get that slab pushed down quickly. And let me go to all, and look at what happened right after the BC free. What do you think that stuff is right there, that yellow? You able to see that? What do you think that was? That was the shared text. When I did the drop caches or BC free, it threw everything in the cache away. Let's do a cat on /proc/meminfo. And the slab now is down to a reasonable size, 142 meg. And my cache field went down to 60 meg. If we'd watched close enough, we might have actually seen it get to 0 and then come back and start reading shared text back in. But that's what that stuff right there was. Right after BC free, I threw everything away in the cache except dirty write back NFS unstable. And then I immediately have to read all the DSOs and executables back into memory again. Any questions? Let's see if we can catch that on meminfo. I can't even get down to it to see. I wanted to see if that was truly a 0 there. Did it go down to 0 itself? In other words, everything was thrown away. Let's see kswap D. So we do see a page free that occurred there as we cleared up that page cache file that was inactive. Again, by default, Linux is going to leave it in cache and only throw it away when that memory is needed by something. Nothing else going on, no trims or anything like that visible here, just a drop caches. Node info is also showing all that memory evenly spread across the nodes got cleared up again. And our NumaLink traffic is also showing. Let's see what we got here. I'm trying to get a correlation here. And this NumaLink traffic actually looks like the I/O right after the trim was done. And one of the things I might do in this case is go to the number of samples, and I'm kind of losing it. I should have recorded it. And that's too fine. I wanted to see, I'm trying to correlate. Let's see, I needed samples. And I just kind of can't see it anymore. Lost the data. Unfortunately, the data that's being put into PM Logger is a 5-minute sample. So I kind of lost the sample that I was looking at there. But I was trying to see a correlation where that NumaLink traffic actually went up around the reads into the page cache of the DSOs and executables that happened. That's what I suspect that was the reloading of the cache from disk. Any questions on this? Now, I have my own little script here. And Brian, you probably know Gus. Gus he has modified the script a little bit. I've got a script called memstat. And it's just taking the meminfo file and turning it into a SAR type of report. The newer one that Gus has puts a timestamp in there and also prints out this header after a while. But this is just a simple widget so that I can actually see what's going on here. So this time I'm going to write a file. And here now we can see that that data, by the right to the application, we have dirty growing. And we should see it go to write back here fairly quickly. Let's see if I can catch this over here as well. We'll go to meminfo. So there I can see the dirty. Let me get the slab back. Let me get free back. So there's my dirty memory going on right now. And in fact, now I can start to see some flushes going on as well. And there would have been disk activity associated with that flush. Let's see if I can catch that here. And there was the writes from a quick flush that occurred there. I'm going to get rid of free. And in fact, we can see here now, here it went dirty. And then right after that, right here was a flush. But we can't see it. Let me get rid of the other statistics here. Get rid of dirty, get rid of a non, get rid of the cached, get rid of the slab, cache clean. I'm trying to get just the write backs right there. So there's the write backs going on. Oh, I need to get rid of mapped. There we are. So there is the flush that occurred there. Now if I put my dirty back in, take it out, so you can see flushes are occurring on each one of these where the dirty went down. And it then goes to write back, and then it goes to cache clean. So here you can see the flushing going on. You really can't see the write backs, and you shouldn't. So here I had some write backs going on here, and again I'm trying to trickle flush and get these write backs going on in the background. So now I'm able to see the data go from dirty. You can't see the write back, but then it's going clean. Let me break out of there. Where was that? See if I can write into that file. So this time I'm writing into a different file system. That's an NFS file system. I want to see what happens here. And again, if I don't have a GUI, oops, that's what I do with this memstat script, is to be able to watch it more closely. It's a fairly simple script. But unfortunately, SAR doesn't help me. Oh, look at, we just had a big flush here where a whole bunch of dirty data got marked to flush. There's a flush daemon that does that, and then it got marked as write back. Let me bring up top. And I'm waiting to see a flush daemon. I'm going to do an I. There's the DD, and by the way, the DD is sleeping now, and we're showing wait IO on that DD. Let me quit out of here. PS-EL, rep for DD. So there's that sleep on that's going on here. DD has gone to sleep. I'm going to do a PS-E-O for options, command, comma, WChan, and grep for DD. And the actual lock it's on is, again, that sleep on page. So this process is sleeping. Let me go into crash. Since it's sleeping, the WChan shows the routine that it's sleeping from, but I want to see the entire stack trace. There it is. I'm going to do a BT on 23113. And there's the whole thing here. So we've got a write going on. It's going off to NFS. Tried to do a generic write begin. It had to grab some page cache. And then it looks like it did a wait on page bit. And here's the sleep on page. And then IO_schedule. Now this kind of stack trace is going to vary with each kernel you get. I'm not used to seeing sleep on page. That is a new routine that I'm not used to seeing that one. Usually it's get request, sync page, block congestion, some of those types of routines. Anything that is IO_sched is what will show up in the top display. So let me quit out of there. Do an I. I'm going to do a Shift W just to save that. So anything that is that IO_sched lock, and this is the routine above it, will get counted as wait IO. And again, if I have multiple things, I could write a T into proc sysrq-trigger and look at the trace back for all the processes that are sleeping on the system. You're either running, runnable, or sleeping. Any questions right now? Let's see what we got here. So, oh, look at this now. So we were writing to an NFS server, and we saw it going dirty. This is about where we started writing to the NFS server. We see the dirties go up, and then right here, huge write-backs this time because the NFS server is not as fast as a direct attached disk. And now we see stuff going into NFS unstable. So we now have stuff being written off to the NAS server and is flushing to NFS unstable. And also up here, notice that the cache is growing. So this thing is also going from dirty to write back to NFS unstable to clean. Any questions on that? Let's look at NAS cache server. So I'm just going to bring up a top. I do see an NFSD. Oh, there we go. We've got a flush daemon going on here. I also have memory management happening here, memory trims or something. Looks like I got little memory available. There's the flush daemon. Oh, let's catch it again here. Memory management trims going on. Here, flush daemon. That's a major minor number, 8:0. If I do a more on /proc/partitions, 8,0 is SDA. I can also do an ls-l on /dev/SDA, and you'll see the major minor number where the size field typically is. I'm going to bring up top disk here if it's available, not available. Let me do a star-dp 1-5. And by the way, LSCSI, I do have a RAID device on this system with failover paths. I'm not going to get into that right now, but SDA is the drive that I've got hot right now. So let me do a star-dp 1-5 pipe grep for SDA. And I can see that my root drive is about 100% busy here, and we're taking 2-second waits. Average wait time, that's about 2 seconds, 3 seconds for an IO operation to get to that disk. Any questions right now? So there's the file that I was writing. What do we got here? About 8 gig right now. And it looks like we had another flush go on here where And I'm not sure why we actually dropped here, but we're going dirty to right back to NFS unstable. The NFS server took a whole bunch of that right back, and now we're doing it again. So there was an NFS flush that happened here. But I'm not sure why the total cache size went down up here. That's not exactly, and it's basically what went with right back. I'm not going to worry about that right now. Get everything else back in. Let's see what NumaLink is doing now. Notice that the NumaLink is still pretty low. Network traffic is on blade 0, and that's what we're seeing here. That's stuff going off to the NFS server. Node info, we can see slabs shrink here, but I can't really see any growth or anything like that. K-swap D, I don't see any trims. I do see some page freeze going on. And what's the other one there? Page allocation. These are page allocates. And then this was the big picture that we were looking at. Let me kill that DD. It's a non-interruptible sleep state, so it's not going to get killed right away. Oops. So if I do a PS-E and grep for DD, well, I want a -L as well. It's in a D state, which says I cannot interrupt it. So that thing isn't going to be able to get done until what? When do you think that program will be able to break out? Let me see if I can even kill it. Kill -9 on 23113. Can't be killed. Let's see if we can look at it with crash. There it is, BT on 23113. And it's, even though we sent it a kill, it's just still sitting there in this IO SCAD sleep on page. So I'm trying to kill the thing. Let's get rid of free. So here I can see my right back go to NFS unstable. Had a flush where it moved it off the mainframe to the NFS server. Another one here. I want to try to catch this if I can. Still in an IO_SCAD. Let me see if I can catch it here. Nothing going on there. Let me quit out of here. Memstat, not in my path. Let me go into bin here. Oops. By the way, this CP now is going off to the NFS server as well, which means it's got to contend with the other activity here. What if I actually try to log in right now? Okay, that one worked fine. This time let me go in as guest. Oh, here's what I mean by not SUing, logging in as guest or something and then SUing. We are now experiencing the NFS bottleneck on the system. So I've got my system kind of tied up. What's going to clean this problem up? I can't get logged in. My NFS paths and everything are in a way. Waiting for somebody to suggest what's going to actually clear this up. We're getting close. Let me get rid of cache clean. What am I waiting for?
For the process to get out of a sleep state, I imagine.
Yeah, but what's it waiting on? The flush.
So a BC or a.
I've got a flush going on, the flush demon and stuff, and we're getting real close. I got to get rid of all the dirty data, the write-back data, the NFS unstable data in memory before that process comes out of it.
So you're waiting for the ratio to hit the ratio.
Not ratio, just the flush, the sync. The sync has to finish before I snap out of this. It's in a non-interruptible I/O state. So we can't kill it until the dirty, the write-back, and NFS unstable are gone. And it has flushed.
Right, but the flush activates when the dirty background ratio hits
yes.
the threshold.
Yeah, that's kind of another topic, Brian. But, yeah, we could do a sync command, or there are sysctl parameters to say when to start the flush. This is something I don't like on these big memory systems. I don't want to see, there we go. We got our response back. The kill came in finally. Remember, I tried to kill it and it wasn't even killable until all that right there. The dirty, the write back, and NFS unstable were gone. This is another problem. If I'm logged into a system through the serial console, 32 terabyte machine, and I got 16 terabyte of write back data, and I do a sync command, or maybe I've got a 100 gig slab and I do the sync command, that window, that serial console and the sync command may not return back for an hour or two until the flushing is done. Okay, let's just do a sync. Oops. And everything's fine there. I'll put this in the background. Run this again. So there I'm writing. This time I'm seeing it in a GET request. I'm just kind of used to knowing what type of library calls I typically see. But there is a GET request call in there. Sync page, GET request, block congestion. Some of these are IO_sched that would show up as this IO wait time. By the way, right now I'm seeing some system time. I want to just see if I can catch that system time. Having some troubles here. There we are. So here again, I'm in that raw spin lock IRQ save. I'm also seeing it trying to allocate space. Some journaling activity because we're growing a file in a extended 3 file system maybe. Bring up top. There's that DD. Notice right now there we went to sleep. There's the GET request I mentioned, and even the wait IO time went up with that. They're both in GET request right now. I wonder if I can catch that. Hard part is being able to see everything at once. Let me put cache clean back in. So here we can see the dirties and then a flush, the dirties and a flush. And what happened here? No space left on device. I'm in trouble now. My home is full. Let me go into var temp here. I've got some files. There is a memory leak or a disk space leak in the jobs that I submit. They generate 10 gig files but don't remove the files when they're done. Which, by the way, while this is happening, I should be able to see my cache clean as I remove these files if they are in memory still. Okay, things are getting bottlenecked here. cs-el. There's that RM command is also on a sleep. There, we got the RMs back. Let's see if we can catch the cache being freed. I didn't see anything cache being freed here. And again, I've got other stuff that's kind of burying that. Let me do this kill all DD. Let me do it with a -9. Oops. Looks like it finished. Because it hit no space left on device, so that one finished. df-h. I got 56% of my space back. Again, I still have a 25 gig cache. None of it is shemem. So if I go into home guest, this is where I was writing those NFS files. I'm going to remove this XX file. And now you can see what was in the cache being thrown away as I remove the file. Looks like the file got removed, and I still have stuff in my cache field. Let me do a BC free-A. And now I can see all that cache being trimmed. Let me go to disk activity. Now these numbers are so big I really can't see the read that might have occurred right here. In other words, reading in the DSOs and shared memory are buried by accounts that are in the 500, 600 range. So it's kind of lost in the noise. Let me get rid of the writes. You can kind of see a read right here, which was the DSOs being read back in. Again, because of these things, let me try my samples. And right there you can see some of the ISOs that are read back in right after the BC free. So now my memory is healthy. My system is basically back to a normal state. Any questions right now? Okay, I want to take a look real quick. I'm going to go to Floyd 2, see what's going on there. Star 1-5. Again, I got 65% of my CPUs being used in user space. One thing I want to do here is a perf top. And I can see that most of that CPU time is in what looks like a random number generator. Code 903 is just populating an array with a random number generator here, _random, coming out of glibc. And code 903 is the one that's doing this. So that's where all that CPU time that I'm seeing there is. Not seeing any real system time in there. No I/O wait time. Let me check memory, star-r 1-5. So I've only got 4 gig in the system used. Only 3% of my memory is being used. Let me cat/proc/mem info. So I don't have a whole lot of shemem going on right now. No dirty or write back. No NFS unstable. And my cache field here is at 8 gig, but again, we don't know if that's active or not. I'm going to do an LSOF pipe rep for regular files, and a sort, N for numerical, B for ignoring blanks, R for reverse sort, K on the 7th column of the report. And the only thing I'm seeing again is pulse audio. Now, you've got to be careful about this tool. You got to know when to throw the data away, meaning that it's not useful. If I did this, I might get things at the top that aren't regular files and really have no meaning. So we'll have to see what goes on there later. Okay, SARD at DP 1-5. So my memory was healthy and my disk looked healthy. IPCS-AM. I do have an unattached shared memory segment here that is accounting for 10 meg. Not too bad, pretty small. Not going to worry about that right now. Again, I'm not sure what's going on here, why this is showing unattached so big. I'm probably not going to report it, but I can't figure out why there would be such a big number like we had before. That seems unusual for this kernel. Again, every time I run the class, I'm using different kernels. But let me do a top now. So there are all those code 903s that we saw. They've been running for quite a while. And one thing bad here, 100% CPU utilization. They do look like that's productive CPU time. Let me pick that PID there, 13580, perf record -P 13580. Now I am periodically sampling the program counter for just that one PID, and by default is writing the samples into a perf.data file. Now we're going to get back to this after break. And I'm just kind of letting it run for a minute or two to see what it's showing me. And now I can see it wrote 24,000 samples. It looked at the program counter almost 25,000 times and wrote it into a perf.data. So now I can do a perf report. And once again, that program was all in this random number generator here. And there was a little bit of system time to it as well. Here's my CPU scheduler. Here's updating the load level, by the way. That's the load level. Some sort of clock interrupts. Again, we still see that raw spin lock and interrupt handlers in here. But again, my system time was real slow, real small. Unfortunately, perf can't get to a line number. Okay, I'm going to bring up top again. And what else do I want to do? That pretty much covers it. Notice that the reservation is pretty much the virtual. They're getting what they asked for, 65 gig. IPCS-AM. I'm only getting 100 meg there. Not sure why I'm seeing these code 9s are 64 gig in size, and they're using an attached shared memory segment, but I'm not seeing it there. Let me check something here, proc mem info. And since it's attached, it should be showing up there, and it isn't. And let's see, where's the shemem? There's something funny here as far as I'm concerned. I'm not going to worry about that right now, but I know that those things, they may not have fully allocated. They've been running for a while. I wonder, and they're generating with random number generators. Let me do an S-trace on one of them. I don't expect them to be doing any system calls. So if they're not doing system calls, you won't see anything in here. They're in pure random number generation. Well, I know that these are shemem segments, but I'm not sure why it's not coming out that way right now. I was expecting to see this shemem field here much larger. PS-EL, EF. What are they asking for here? Oh, they're small in their memory sizes. They're only asking for 100 meg. but they have reserved, and for whatever reason, it looks like they have a memory resident of 65 gigs. That is not exactly what I was expecting. They've touched more than they should have. Again, I'm not going to worry about that right now. Let's do a kill all code 9 GNU 03. Let me go into home guest real WL. If you take a look at this code 9.c, we're passing into it two arguments. The first argument is the size of the shared memory segment. The second argument is the SHEM ID key that we want to use. And then we passed in the key and we say, get that key and get the ID for it. Oops, where are we? And we're going to create it here. If we have an ID, or if we don't, if it's less than 0, in other words, negative, then we're going to basically down here attach to it right here, and then just go through this and random number generator populate that shared memory segment. And I have commented out the SHEM detach so that this deliberately leaves unattached shared memory segments. So those are gone. IPCS-AM. So that makes sense. That's correlating right. cat/proc/meminfo. And mapped is down. And shemem is down. That's 100 meg there. Okay. Clear shemem. Oops. Oh, I didn't put it on this one. Home guest bin. Clear that up. cat/proc/meminfo. And all my memory's free. At this point, we need to take a break. Any questions on that right now? Were you okay with that, Camille? I haven't heard from you.
Yes.
Okay. I've got about 5 minutes to the hour. Let's come back in 15 minutes.